Okay, I'm happy to be here to talk about some of our progress and mainly actually focus on how we think about to engineering colloidal quantum dots for micro LED displays. I'm currently a postdoc in Moungi's group. Um, so we have excellent speakers talk a lot about AR/VR glasses, and more formal way, it could be the next generation of technology that really change you how you interact with the surrounding environment. But I more personally, I'm a video game lover. When I see films like Ready for Player One, I really want to have a glasses like this, and you can interact with the game characters just like you interact with normal people in the real life. So like many expert and business people expect that the VR AR glasses will be a huge deal, at least in the next decade. So the retail technology, micro LEDs, at the conference, people talk a lot about this. And for wearable AR VR glasses, you do need very small LED displays. And this is not only becomes hot in the industry side, but also caught eye by the academia community as well. If you search the website and type in micro LED, the publication actually grows probably around like 1,000 times more compared to the start of this decade. So micro LEDs definitely have a lot of challenges. One big challenge is about EQE. If you take the well-developed LED technology and just trying to decrease the size of the pixels, and you see a decreased EQE with smaller sizes. People believe that this is mainly because of the effect from the surface to effect, because effectively you have a larger surface to volume ratio. And I want to emphasize that there are definitely ways to trying to mitigate this by a lot of companies and research groups. But we are really interested in the another technology, which utilizes a color conversion layer. So basically, in this case, instead of directly injecting carriers into the semiconducting layers, you can have a light, LED light at the bottom, for example, blue LED. And if you have some materials that can absorb blue light and emit precisely the wavelength you want, like red and green, then you can have a full RGB display, basically. We do believe there are several advantages for this approach. First, you could possibly simplify the fabrication process, because essentially you only need one blue light source, and then you can fabricate individually the color conversion layer materials. And because of that, you can also have possibility to enhance color uniformity, because this fabrication of the color conversion layer is separated from the blue LED at the bottom. And finally, it could also you can also have some handlement on the thermal effect. You can place the color conversion layer actually away from the LED. So in this case, you can mitigate some thermal effect. As a material research group, focus on the colloidal quantum dots. We believe quantum dots is really good candidate for this purpose for the color conversion layer materials. So what is quantum dots? Very briefly, quantum dot is basically nano-sized semiconductor, and it had the core is basically some kind of fluorescent semiconductor materials, and you have a shell of ligand. The quantum dot is efficient and bright, which means the quantum dot is really high. You can almost reach 100% for many different compositions, and you have very pure color. The four-width max is really small compared to many organic fluorophores. And one thing I want to stress here is what makes quantum dot unique is that, and all the nanoparticles, is that you have a specific interface between the ligand and core. So in this case, or in most cases, when you modify the surface, you really don't change the optical properties of the core. So this gives you a lot of flexibility to make this particle comparable to the environment or surrounding medium if you want to make it into some other applications. So generally, we synthesize quantum dots using a hot injection method. We have a reaction pot contains precursors and ligand, and you heat up into a certain temperature, and you hot inject the other precursors. So in this case, we can have a very precise control of the size of the the particles, which give you a precise control of where it absorbs and where it emits. So this using quantum dots as display or LED is not a new concept. People have already developed into real applications for different compositions. For example, lead, early years lead or cadmium-based, and now people shifted to more indium phosphide and zinc-based quantum dots because of less toxicity. So we have a great introduction of the problems by one of the meta speakers. So in this talk, I'll talk more about how we think about to overcome these challenges. Most of them has been covered by the speaker before. For example, we're going to play with the synthesis to increase the absorption of the quantum dots. And also we're going to look into the spectroscopy to see what's the thermal stability cause, what's the reason for thermal instability and also the multiple exciton behavior. And finally, I want to give some time to talk about the real fabrication process, how to make this quantum dots really compatible for different fabrication process. So first, why we care about the absorption coefficient, how it absorbs light. So basically, if you have let's say blue LED as a light source and you have copper convolution layer on the top, if it's very, very thin, then it absorb enough light, then you have blue color leakage. This will compromise your color purity and reduce color conversion efficiency. Also, you cannot make it like infinitely thick to make it no blue leakage, because basically this thicker film is always going to be hard to fabricate in a very uniform way. And also, making it thicker just gives you more chances to create more defects and more scattering centers and create non-radiative losses. And finally, especially if the quantum dot doesn't have 100% yield, you also need to consider the reabsorption and reemission process. So this also brings down your color conversion efficiency. So what do we think is the solution, or how to mitigate this thing? So first, in order to increase absorption coefficient, our first thinking is trying to conjugate to some light absorbers. So if you're careful about their spectral overlap, basically this light absorber, the emission spectrum overlaps with the absorption spectrum of the quantum dots, you can have anti-transfer between them, and this actually brings up your absorption for the whole system. So actually, Blue Ridge Group and our group published a paper in 2009, actually bring this J aggregates in close contact with quantum dots, and this is the excitation spectrum. You can see a sharp increase or effective absorbance of the light by the J aggregates, and if you excited the quantum dots or whole system around this range, you can get 5 times enhancement of the PL, which is caused by the enhanced absorption. So you may argue that this is very narrow. So we do want a broader absorption band in a whole blue range. So we can take care of this like well-developed organic dye field. There are a lot of dyes designed and synthesized that can cover a large area of the blue range and emit at in the range of the blue as well. And we are currently working on synthesizing highly fluorescent indium phosphide-based quantum dots, and next step will be conjugate this dye to the surface, because this is an energy transfer process. We want to have a precise control of the distance between the dye and the quantum dots. And the second strategy we think about is plasmonic enhancement. We want to have some metal structures close to the quantum dot surface, and it could go through 2 different mechanisms. One is these metal structures can also absorb energy of photons and translate into oscillated dipoles, and these dipoles can also translate energy to the transfer the energy to the quantum dots. So this is more another way of seeing it as a light absorbers. The other way is enhanced emission, which we call the Purcell effect. We can have enhanced radiative rate. So in this approach, the distance will be very, very important for the system, because if you get too close, you might see carrier transfer or carrier hopping from the quantum dots or metal to quantum dots and really quench your emission. So in this case, we believe we need to have some spacer in between the quantum dot and metal structures, and this spacer can help us to engineer the distance between the quantum dot and metal structures, and this spacer also modify the dielectric constant of the surrounding medium. And if we are careful and choose a dielectric constant shelling between the air and the quantum dots, you can effectively see it as like a coupling system, so that you can also efficiently coupling light. So the next part is about spectroscopy. So there are several related problems that we think that really should be we consider when we utilize these quantum dots for micro LED applications. First is people reported that on the micro LED you really have a high incoming photon flux, which probably reach around like 10 watts per centimeter square. And it's known in the quantum dot field that if you have a really high income flux excitation light, you will see another peak really comes out on the side, which is actually the formation of the multi-axons and the emission of it. There's a good literature actually doing a lot of relative studies, and based on their measurements, the 10 watts per centimeter square lies around in this range, and you can see the biexciton intensity is almost at the same scale at the compared to the single exciton. So this is something that we need to care about when we engineering the quantum dots. And also the other effect from the multi-exciton as well is OJ recombination. So in this case, instead of emits the photon out, it actually excites another exciton into a high energy level, which doesn't give you light. So this OG recombination is also being considered one of the major losses, losses or reasons for the intensity roll-off for the normal quantum dot LED as well. So overall, all these multi-exciton behavior are really highly related to the electronic structures, which eventually goes to how you build these core shell structures, the thickness and the core size, the shell component. So we're going to have a more detailed understanding about using interface engineering and shell engineering to understand and optimize. Basically, the idea is trying to optimize the bias-on quantum yield, but also minimize, at the same time, minimize the OG recombination rate. The second part is thermal stability. In the quantum dot field, it's known that if you increase temperature, especially in air, it quenches emission. And people report that for the micro LED, you probably can reach over 100 degrees under operation. So there are tons of reasons or people propose mechanism behind it. This is more on the cadmium side. You can have surface defect, which the electron will be trapped on the surface, or individual defects, which on the core shell materials that on a high temperature you'll have some substitutional defects, or some people argue there are some temporary traps that the PL can recover on when back to the room temperature. So combined with the spectral studies, we can actually first understanding for the indium phosphide quantum dots, for example, what's the real mechanism, and trying to find a way to find a solution to it. For example, if it's more on specific surface defects, we can find ligands to passivate that defects. If it's, some people argue that it's actually degradation of the organic ligands, then we can change the organic ligand into the inorganic ligand that will sustain under 100 degrees, for example. So finally, I really want to have some time talking about the fabrication, because this is, after we make this material, the final step is trying to really make them into films or product that we need. And a lot of people mention that for the AR, VR glasses, you do need a really, really high PPI. This gives a lot of limitations and difficulties on how to process these particles. And photolithography is well developed, very well developed in semiconductor process at this point. And what if we can just mix or somewhat make the quantum dots compatible to the whole process, basically making a quantum dot photoresist that can do all the lithography that's well developed at this point. Again, I think I want to emphasize again for this is the uniqueness of this material. The surface and the core material is, you can think of it's kind of separated. you can modify the surface so that it's comparable to the photoresist that you need, and then you can do the whole process just like normal photolithography. So there are definitely a lot of strategies to do it. If you don't want to really make doing like a ligand change, then you can formulate your photoresist inks and then just trying to mix them and make a stable photoresist ink. Or if you want to play with the organic reactions, you can actually ligand change the surface into some, for example, photo cross-link ligands. It polymerize under specific conditions, for example, UV light. Or if you care about the packing density and really don't want any organics, you can also change all the organic ligand into inorganic. Some inorganic ligand pairs can solidify under certain conditions as well. For example, this E-beam lithography. Overall, we're collaborating with Professor King's group. We're like functionalizing quantum dots with specific ligand that's compatibilized with specific inks, and hopefully can be utilized for the photolithography for the further processes. So finally, on to thank Moungi and whole group, and we have collaborations with actually many different departments in MIT, from electrical engineering to mechanical engineering to the MSc. We believe this huge collaboration will really bring this field forward and make quantum dots micro LED a real thing in the future. So that's all. I'm happy to take questions.
Thank you, great presentation. Do you do any infrared quantum dot?
Yes, we can do infrared. This is mostly lab-based, of course, and indium arsenide, those things, yes.
Up to what wavelengths? Can you go to like 3 or 4 micron?
Yes, as far as I know, like for the lead cyanide or even lead telluride, you can go, yes.
Thank you. Thank you.
Very nice talk, Hua. Very interested in your quantum dot photoresist. What's the maximum packing density that you think you can get into these imageable materials?
That's a good question. So we haven't reached that step, but in terms of, if you think about packing, the highest packing density for the like dense packing is around like 70-ish%, and then you have some things, organics in between. So this could you bring down even less packing density, but you can find ways to overcome this. For example, if you change the shape to like 40 cubic, it possibly goes to like almost 100% in theory. And also you can try to get rid of the voids without using organic ligands. So if it's fully inorganic, the distance between the particle could be minimal. So yeah, could reach really high number in theory.
Very nice.